So looking at example 6, we're still in that section 4.4, right? Related rates. So a right circular cylinder is changing shape. The radius is decreasing. First of all, right circular cylinder. So we're talking about like a can of pop or can of food or whatever, right? That's a cylinder. The radius is decreasing at a rate of 2 inches per second. So that means we're given the derivative of the radius, right? So the derivative of the radius with respect to time, since it's decreasing, it would be negative 2 inches per second. And then it tells us the height is increasing at a rate. So here we know, since it's a rate, it's the derivative of the height with respect to time is 5 inches per second. Now it's positive because it's increasing, right? Does that make sense so far?
Yeah.
All right. When the radius is 4 inches and the height is 6 inches, how fast is the volume changing? So if I'm wanting to know how fast the volume changes, I'm wanting to know the rate or the derivative of the volume. Is that fair? Specifically, when the radius is 4 and the height is 6.
Do I go, or are they going to close it?
We release at 12:55 or whatever, 11:55, whatever time it is, 10:55. The 55. All right, so here, this is your radius, and this is your height of a right cylinder, yes? Anybody remember the volume of a cylinder? Oh, it gives it right there, never mind. We don't have to remember it. I think most of those will be given to you if you need them. So, having seen that, having known what we're given, as you're reading through those, if you write down what you know, it isn't terribly difficult. Is that fair? So the first thing we need to do is what?
Derivative of v.
So dv over dt equals, now we're going to have to do the product rule, aren't we?
Yeah.
So we would have what? 2 pi r h dr dt. Is that fair? If we took the derivative of r first.
Yes.
Plus, if we take the derivative of h, then we'd have pi r squared.
At this time, please release the seniors for their PSL in the pack.
dh
Thank
dt.
you.
You guys can go, or let's finish this and then you can go. Because we're really close to being done. All right, so we have the derivative there, yes? And so now, all we have to do is substitute in, right? So dv dt equals 2 pi, our radius is 4, our height is 6, dr dt is negative 2, and we should probably be putting our, this is inches, inches, inches per second, and then plus pi r squared would be 4 inches, and that whole thing squared. dh dt is 5. So then here you're just multiplying. That'd be 24 times 2 is 48, times negative 2 is negative 96 pi. And you'd have inches cubed over seconds. And then here 4 squared is 16 times 5 is 80 pi. And this would be inches squared times inches is inches cubed over seconds. And so you can see there your derivative of the volume with respect to time when r is 4 inches and h is 6 inches would equal negative 96 plus 80 is negative 16 pi inches cubed over seconds. questions on that? So since we only have 2 examples left, I'm gonna go ahead and do those on this video, and then I'll post it. So if you wanna take the notes over the next 2 on the video, you can. Probably wouldn't be too bad. And then if you guys have extra questions, just let me know. Make sure 4.2 is turned into the box though. Okay, yours is already there.
Yeah.
So I think that you'll probably be okay with these last 2 examples, doing them on the video.
Okay.
And then you need to be working on your 4.4 assignment. Hopefully you've done some of it.
Yeah.
Yeah? Okay. If you have extra questions, then we can maybe have some time, maybe Thursday or Friday.
Okay.
Okay? But I will go ahead and do these examples in this video, even if nobody's here. I'll do it to myself. Would you shut the door?
Yes.
Thank you. All right, so in example 7, an inverted cone is leaking water at a rate of 1 centimeter cube per minute. So the cone is leaking water. So that means the volume is decreasing. So the derivative of the volume, I know that, is leaking water at a rate of -1 centimeters cubed over minutes. The cone has a height of 9 centimeters and a diameter of 6 centimeters. Find the rate at which the water level is dropping, specifically when the height is 3 centimeters. So here we're given this volume formula of a cone. We have an inverted cone. So what I'm looking at here is something that looks like this, with a radius here, and your height is here. So it says the height is 9 and the diameter is 6. So if the diameter is 6, then I know the radius is 3, right? So I know my radius is 3. That doesn't change. The radius of the cone does not change. Okay, so then what we're looking at is I'm going to just kind of draw this triangle that it's formed here. If the radius here is 3, when the height of the whole cone is 9. Now, as this is decreasing, as the water level's going down, our radius is going to change here as the height changes here. But it's going to stay proportional. So if we think of our radius is 3 and our height is 9, so radius over height. I'm wanting to know, find the rate at which the water level is dropping. So if I'm finding the rate at which it's dropping, I'm trying to find the rate of the height. So that means I'm finding the derivative of the height with respect to time, specifically when the height is 3 centimeters. Now, if I was to do the derivative of this, I would end up with dr dt and dh dt. I don't know dr dt. I do know that I'm trying to find dh dt, and I know dv dt, but I can't have 3 different rates if I only know 1. So, can we get the radius in terms of height so that when I do the derivative, I only end up with dh dt? If we think about it in terms of this, here we could say this is 1/3 equals r over h, right? And so then 3r would equal 1h, and my radius would equal the height over 3, or 1/3 h. So the reason I'm doing that's because I don't have, and nor do I need, a dH dt. So I've got to substitute something in here to get rid of that r so that when I do the derivative, I don't end up with that rate of the derivative. So I'm going to substitute in. I'd have v equals 1/3 pi. Instead of having r squared, I'm going to have 1/3 of h squared, and I still have times h. So I know 1/3 squared is 1/9, and 1/9 times 1/3 would be 1/27 pi. H squared times h would be h cubed. So that's what I'm going to use for my volume formula, is 1/27 pi h cubed. So now when I do my derivative with respect to time, I'm going to get what? I bring my 3 down. 3 over 27 is going to be 1/9 pi h squared. I'm only going to end up with that dH dt, which is what I need because I have a height, I have dH dt. I don't have dH dt. I need to find dH dt, but I have dV dt. So I could substitute in at this point. dV dt was -1 centimeter cubed per minute equals, I'm going to write pi over 9 instead of 1/9 pi, times h was given to us as 3 centimeters. And then that was squared. So 3 squared. And I'm trying to find dH dt. Well, 3 squared and 9 would cancel. And this would have been in what height would have been centimeters squared. Correct? So I would divide by pi centimeters squared, or here I have -1 centimeters cubed over minutes equals pi centimeters squared dH dt. To get rid of this, I'm going to multiply by 1 over pi centimeters squared. Multiply by 1 over pi centimeters squared. Here, my centimeters squared, my centimeters cubed would cancel. I just end up with centimeters. This cancels. So I end up with dH dt when h is 3 centimeters equals -1 divided by pi, and it would be centimeters per minute. And you could find the approximation too by doing -1 divided by pi. And it's going to give you approximately -0.318 centimeters per minute. So the key to that one was to not do the derivative of the volume right away because we didn't know an R. It did not give us that piece of information when we were trying to find this. And we don't know dr dt. So let's look at the last example now. Example 8. A lamppost is 26 feet above the sidewalk. Andy Great excuse me, is a 6-foot-tall calculus teacher. And is walking away from the lamppost at a rate. Excuse me. Okay, walking away from the lamppost at a rate of 4 feet per second. So he's walking away here. If I'm calling this x, then the rate that he is walking this direction would be dx dt would be 4 feet per second. It's positive because the distance is increasing from the lamppost. When he is 20 feet away from the lamppost, find each of the following. All right, so I'm going to have to come up with some sort of equation to begin with. And it's talking about his shadow. So the lamppost is going to cast a shadow, and this right here, let's see if I have a different color I could use. This right here would be his shadow, right? And so if I say y is his shadow, then I'm asking how fast is that shadow changing. So I'm trying to find dy dt, and that would be the rate the shadow is changing. So to me, it looks like I'm going to have to set up a proportion, the big triangle versus the little triangle. So if I think of the big triangle, we know this is 26 feet tall, and then this whole long side would be the distance from the lamppost plus the shadow, so x plus y. And then the little triangle would be the 6 feet and the y. So when you set that up, you can set it up multiple different ways, but if we set up 26 feet over 6 feet, then that would be the big triangle over the little triangle. So then the big triangle would be x plus y over the little triangle's distance would be y. So I'm just trying to come up with an equation here to relate my rates there. So here I can cross multiply. I would get 26y equals 6x plus 6y. I can subtract 6y to get my y's together. I would get 20y equals 6x, and I can divide by 20. So y equals 3 over 10x. So I had to come up with that equation to relate x and y, and I have my dx, and I need to find dy. So the derivative of y is going to be dy dt. Here the derivative of this side would be 3/10, and the derivative of x is dx dt. And so then here I'm trying to find dy dt, so I can substitute in. So I'm looking for dy dt, and this would be 3/10 times, it told us dx dt was 4 feet per second. So that would be what? 12 over 10 or 6 over 5. And what are we talking about? We're talking about the rate at which the shadow is changing. So the rate at which the shadow is changing would be measured in feet per what? Second. Therefore, Andy's shadow length, that's what we were trying to find, is changing at a rate of 6 feet every 5 seconds. So it was all based on what we're given in the problem. dx dt is 4 feet per second. We know we were trying to find the rate of the shadow, dy dt. We had to come up with an equation somehow. And so my knowledge of proportions with geometry helped me out there. All right, so now it says at what rate is the tip of his shadow moving? How does that change things? At what rate is the tip of his shadow changing? So we're talking about this right here. At what rate is that tip of the shadow changing? Well, the tip of the shadow was given by x plus y. So I'm wanting the rate of x plus y. I'm wanting d of x plus y with respect to t. So if you think about that, we know this part was x, and we know this part was y, right? So would it be fair to add the rate of dx dt and the rate of dy dt? If we added those two rates, would that give us the rate of this tip? We know that this is a property where we can do the derivative of each of those. So that is what we're talking about, the derivative of each of those added together, which makes sense in the picture, but also makes sense when we're talking about derivatives. So we're trying to find the tip. We knew that was given by x plus y. That's how we would get to the tip. And so you can actually separate those out. So we know dx dt is 4 feet per second. And we know dy dt, we just found it. It was 6/5 feet per second. So what would that be? In terms of 5, that would be 20 plus 6 would be 26 over 5 feet per second. Therefore, the tip of Andy's shadow it's positive, so it is increasing at a rate of 26 feet every 5 seconds. So that is related rates. Okay. On some of these on your homework, you may have to look up the formulas. I think we probably did most of the formulas in the notes. But some of them you're going to have to find an equation for. So this one's going to be very similar to what we just did. We talked about cylinders. You're going to have to draw a picture for that one and figure out what we're talking about on that one. Distance and rate and time, you're going to have to use that for 9. Isosceles triangle, we got to remember those things. Okay, alrighty.